Okay, let's practice together. First off, we have an alkene adding metachloroperoxy benzoic acid, adding peroxide, so you're going to get the epoxide ring, so epoxide synthesis. Okay, and enantiomer, so the oxygen can be at the top and at the bottom phase. The next step, so we have an sodium alkoxide, which is a strong nucleophile, and a strong nucleophile will go SN2, go to the least substitute carbon. Okay, so that's SN2, and the enantiomer we go to is enantiomer. All right. Next one we have, okay, if you recognize this is halohydrine formation, okay, halogen and water formation basically. They're adding chlorine, you're gonna get two chloronium ion. One of them gonna point up, the other one gonna be point down. That's enantiomer. Okay, so water gonna go open the ring, so you get that, and the one that chlorine that point down will lead to the other one. So, all right. And then, all right, next one, sodium hydride. This is similar to Williamson synthesis, adding sodium hydroxide to activate the nucleophilicity of hydroxide ion. Okay, or hydroxide, so you become an oxide ion, right? And then intramolecular SN2. So the top one should go to that, and the bottom should go to is enantiomer. Yeah, they all have enantiomer here. Next stop, we get, okay, another peroxy acid. Can you see that? That's O3 right there. Carboxylic acid, COOH. This is O3. This is peroxy acid. And it's going to be epoxidation. Here we go. Add an epoxide. Right? This carbon is not a chiral center. Don't have to worry about it. So just one product there. Next stop, we got sulfuric acid. So this is in an acidic solution. Adding phenol. This is phenol. A benzene and an OH. Okay. Adding sulfuric acid. What does it do? Well, make this compound more acidic by protonate on the oxygen. Okay. And in this case, we have tertiary right here versus primary, right? So tertiary, we have become more electropositive. So phenol gonna attack right there. Here we go. That's phenol at the more substitute carbon. On the other reaction, the same starting material, but this one is use a strong nucleophile, right? And you don't have to think twice. Strong nucleophile attack right there. The less substitute carbon. Okay, so phenyl group right here, all right, and then down here add sodium hydride and ethyl iodide. This is Williamson synthesis. If some of you recognize it, so hydride will activate the nucleophilicity of hydroxyl group, and then this guy go attack at an ethyl group. Get that? All right. So my point is, I want to tell you, so you don't have to memorize all the reaction. I mean, this is not necessary as long as you know what each one of them do. Right here, what do you call it? Like Grignard reaction? I don't even know how to call it. Williamson synthesis, but well, you don't need to know it, right? You know, oh, there's a strong nucleophile, SN2, attack that, and then quench with water, so add proton on oxygen, or you get that compound. This one, I don't know what the reaction is this, but I know that sodium hydride will deprotonate that hydride, hydroxyl group, become more nucleophilic, and then add a nucleophile. Let's go attack. See that? If you know what each reagent do, you don't have to memorize these reactions. All right. Okay, let's talk about the application of using an ether, the epoxide.